Okay. So, good evening, everyone. I think I don't need this thing. It's just our very nice coffee break, and it's the last section. So just relax. It would be no complicated statement in my talk. So, yeah. Okay. I'm Ivan Mihajlin from Academic University in St. Petersburg. It's the joint work with Alexander Kulikov and Olga Milanich from the same place. And it's about linear size lower bounds for circuit complexity. So at first, I would like to introduce some formal definitions. I know you're all aware about this stuff, but still, OK. We are talking about Boolean circuits. It's directed acyclic graph. And it has n vertices that are associated with variables. And we have some gates. So we have the vertices that are variables. We have other vertices that are gates. It is a place where some computation is going on. And we have some output gates. So the Boolean circuit is representing some function and it's the way of computing some function. We are interested in circuits with gates with only two fan-in and only an unbounded fan-out. So it's the standard definition of some P-poly class. And it is two different basises that I would like to introduce. It's B2 and U2. And the difference is this. The B2 basis is you can compute anything you want from two variables. And U2 is anything except XOR. Actually, the more easier way to think about it is like you have only conjunction and negation for free. So this circuit is B21. And if we cut this one and this one, it's become U21. Fine. Some known lower bounds for this object is that if we pick up some random function, it requires exponential size circuit. And we can't name any explicit function with more than linear lower bound. So, OK. In the full basis, the lower bound best known is 3n. In U2 basis, best known lower bound is 5n. OK. At this moment, I would like to say some words about motivation of this work. It's very simple proof, so I have plenty of time for this. If you heard Ryan Williams' talk, it's about circuit complexity depression. So we want to separate NP and P-poly. That's great. And we want to prove some super polynomial lower bound. Great. And we have no idea how to do this. Just no idea. OK, let's take a little less ambitious. We want to prove some polynomial lower bound, n square, n to the power of 10. And we still have no idea how to do that. OK, let's start with the linear lower bounds. And it still seems very hard to prove high linear lower bounds. So we have exponential one for the random one, linear one for the explicit one. And we can't improve it. And it is actually the only one method how to prove linear lower bounds on circuit complexity. It's gate elimination method. And it seems to be that this method has some very low limitation. So this 3n and 5n looks like very close to this limit. Maybe not limit, but very, very close. So if we are thinking about gate elimination, so let's don't try to prove more higher lower bounds. Let's try to do simpler proof for the limit. So let's try to introduce the limitation of this method with a very simple proof. So this work would be about proving the highest lower bound is known nowadays, 5n for the U2 basis. But we introduce very simple proof. And we introduce this proof for a very simple function, actually for a very simply describable class of functions. Why it is really necessary to get simpler proof? Because the previous paper by Wama and Mitsumi that proved 5n lower bound contain more than 100 cases, and it is very hard to read this one, and you definitely don't want to be actually in all these cases. So we will introduce only 4 cases, so it's 25 beta. Okay, so this talk, I will introduce lower bound for circuit complexity, but I will take small relaxation to get simpler proof. I will not talking about function with one output, but with logarithmic output. Actually, it's not seem to making simpler the proving. It's no known techniques that are dealing with this. So the proof is based on gate elimination method. So we just want to kill 5 gates for killing every variable by some yes. So it's only 4 cases, so it would be very fast, and actually I can give you the whole proof, not just some ideas. Okay, what is the function? The function is the set of linear functions. The set of linear functions is very well describable by the matrix. So we introduce the matrix n by log n, and we want to all columns have some Hamming differences. Okay, why this is necessary? Why we can omit this stuff? Because if 2 variables if 2 columns are explicitly the same, then we can glue these 2 variables and pay only 3 gates for this. So we really need all columns to be pairwise different. So the easiest example of such matrix is the check matrix for Hamming distance for Hamming code. So what properties of this function I would need? That it strongly depends on every variable. So under any substitution for other variables, function still depends on every variable that's not substituted already. So another one, it has some distinguisher property. So we have for every 2 variables, we have the functions that strongly feel the difference between these 2 variables. So the proof. It would be 4 cases. It is constructed very easy. We take the directed acyclic graph of the circuit, so we can make some topological sort of the gates. Let's take the first one, the top gate, and check the variables near this gate. So that variables that are feeding this gate. So it is only 3 possibilities we need to check. It is the fan out of these variables. If we can describe why fan out 1 for the variable is impossible for such circuit. And it is very easy to deal if fan out is high. So the only one interesting question is actually the case number 3. So why, if fan out is equal to 1, it is not computing our matrix? Actually, it's because the conjunction gate losing some information. It's a very simple idea. So we can make some substitution to other variable, to xj, and lose every information about xe. So then, because we have strongly depending on every variable function, it is a contradiction. So this construction is impossible. Very easy. Case number 2. We have some variable, and it have high fan out. So Then we just make the substitution, and as we have two gates with the same type, or two conjunction with this variable, or two disjunction with this variable. So we can pick up 1 or 0 and kill in this case these three, this, and this. Because if we substitute 1 to the x e, then these two gates becomes a constant, and the gates that was fed by these two become constant too. So we are killing five gates. So maybe it's not really clear the method. We make some substitution and killing gates, and we still have the same class of function, so it's still easily induction. So okay, the interesting thing, the case number 3. It is about why we pick up the Hamming-Codd matrix. It's because this construction is impossible. Actually, it is a hard case for many other proofs. This construction losing information about order of these variables. So it's impossible. And we can distinguish this one. Case number 2, it's the only one tricky. I meet the real proof, but the idea is simple. We can make a substitution for one of the variables and kill this through gates. And as we can't have a variable with fan out only one, this gate and this one killed 2. So it is the idea how we can count the 5. It's actually not really complicated, but I have not enough time. So is the case analysis is clear? Seems to be. Okay, that's all. Thank you for your attention. If you have some questions, feel absolutely free. We have plenty of time.
Not plenty, actually, but minutes.
2 minutes. Okay. So, yeah?
What is your inductive hypothesis about your function that when you eliminate these 5 gates, and what is the property that remains?
It's still all pairwise. It's still matrix, and still all the columns are pairwise independent. No, not independent, but different. So we have. No, I just actually the definition is completely the same. It's not the Hamming-Codd check matrix, but it's just an example of such matrices. This property is still the same, definitely by substitution on the constants. Okay. So.
If not, let's thank Vanya once again.